Hello, sir. This is our presentation on our technology discussion paper on the current limitations of optical techniques to generate terahertz pulses. Myself, Jeet Mukherjee, and my teammate Arundeep Singh, who is presently taking the video, and he will be coming at the later slides. He will be presenting this presentation to you. Firstly, what was our main reason of choosing this topic? So, terahertz pulses has been gaining a lot of research in the 21st century. The terahertz pulses have gained reasonably high range of applications in the fields of information and technology, biology, medicals, pharmaceuticals, and agricultural products. The usage of photonics for the generation of terahertz pulses has been extensively used, and it's going on a very rapid research phase. There are very many limitations for the generation of terahertz pulses while by the photonic or the optical techniques. But after initial investigation, we found out the major limitation for the generation of terahertz pulses by optical techniques was angular and material dispersion and absorption. So, what is terahertz pulses? Terahertz pulses is the sub-millimeter radiation, which is an electromagnetic radiation of a wave frequency of the order of 10 to the power 12 hertz. So T waves are actually lie between the microwave and the infrared radiation in the electromagnetic radiation scale. So the terahertz pulses also have a wave bandwidth of zero point 0.1 to 10 terahertz. So the most astounding fact which makes terahertz pulses such reason to such research and stuff is because it's like it can is the only kind of is a kind of pulses which can transfer through or penetrate through dielectric materials, that is plastic, ceramics, pharmaceuticals, and wood. The other main feature of terahertz pulses is that it can be also used with materials to present identifiable frequencies and fingerprints which can be used for security purposes. So, what are the different ways of generating the terahertz pulses? There are actually two major methods of generating of terahertz pulses using optical techniques. The one is optical rectification, and the other one is linear electro-optic effect. So what happens in the optical rectification technique? In optical rectification technique, an optical pump is dispersed angularly for the production of intensity front, which is tilted in respect for the propagation direction. The terahertz pulse radiation is propagating in an angle which is in the tilted front and is also in the femtosecond laser pulses with terahertz pulses of the lithium nibonite, which emerged as the most effective way of generation of terahertz pulses. By this method, production of single cycle terahertz pulses with optical to terahertz conversion efficiencies of excess of 1% room temperature. The next slides of the next type of the generation of the terahertz pulses, that's the linear electro-optic effect, and the papers we have been discussed will be taken by Arundeep Singh, and then I will come again back for taking up the paper 6, 5 and 6 and the conclusion.
Hi, this is Arundeep Singh. I'll be discussing the other method of the generation of the terahertz pulses, is linear electro-optic effect. This method is only applicable for the crystal that are not centrosymmetric, and the electric field of the terahertz radiation induces a phase modulation of the laser pulse. In case of longitudinal linear electro-optic effects, the electric field is applied parallel to the direction of propagation of the optical probe laser beam. In case of transverse linear electro-optic effect, the electric field is applied perpendicular to the direction of propagation of the optical probe beam. Detection of terahertz radiation pulses is generally performed using the geometry of the transverse electro-optic effect, and the sub-picosecond terahertz radiation pulse amplitude and phase of the are measured by recording the phase change of femtosecond near infrared laser pulse, traveling collinearly and simultaneously with the terahertz radiation pulses, sub-picosecond terahertz radiation pulse. The electric field of the terahertz radiation induces a change of the index of refraction of the crystal via the linear electro-optic effect, such that the material become birefringent. And now the review of paper one. This paper gave us the information of the fact that generation of intense terahertz radiation can be done using both optical rectification, which we can say OR method, and laser plasma beam based configuration. It states that for generating and detecting terahertz wave, ZNTE and gallium phosphide crystal are commonly used due to their relatively good matching between the terahertz phase velocity and the optical group velocity at 800 nm. An efficient terahertz wave generation via Cherenkov type phase matching has been demonstrated, in which waveguiding effects for the optical pump and decreased terahertz absorption in the LN crystal to achieve intense terahertz wave emission. This paper has also studied the different experimentally setup for terahertz generation. The first one is title plus front technique. Second one is the two color plasma technique. The third is optical rectification is a large aperture ZNTE crystal. And the major limitation or drawback focus in this paper is mechanism to implement high intensity versatile terahertz sources. It also says that the laser based terahertz generation technique requires a pulse high voltage bias approximately 10 kilovolt in order to avoid excessive power dissipation in the switch associated with DC biasing. It also the amplitude saturate at relatively low optical excitation, which require a very large apertures and very large associated bias voltage to take advantage of high energy optical excitation. In the photonic generation of terahertz pulse, the high voltage switching circuit can produce significant electrical noise. Moving on to the review for the paper 2. This paper directly uh, peritinate to the optical rectification, which is one of the method of terahertz pulse generation. OR of femtosecond laser pulses with tilted pulse fronts in lithium niobate has emerged as the most efficient terahertz generation technique. It is stated in this paper that theoretically predicted conversion efficiency for this approach are larger than those of corresponding experimental demonstration. For example, conversion efficiency of 10% at 100K are predicted for transform limited 500 is full width at half maximum. Pulses centered at a wavelength approximately 1 micrometer. The 1D spatial model, including the effect of material dispersion and group velocity dispersion due to angular dispersion, was presented in this paper. In along with this experiment studied in paper, a 1D model considering material dispersion, GVD-AD, and self-phase modulation, which is also known as SPM, suggested that SPM rather than FCA was the principal reason for saturation of the terahertz energy. Uh, in the aforementioned models, the spectral reshaping of the optical pump pulse caused by terahertz generation was not considered. These effects have not included to explain the dramatic experimentally observed frequency downshift and the spectral broadening of the optical pump pulses. This paper also says that 1D and 2D spatial models, which simultaneously account for cascading effect. The second one is material and angular dispersion. The third one is absorption. Fourth is SPM, and the fifth one is SRS. Now moving on to the paper 3. This paper investigated the application of medicine and biology spectrometric and imaging. It has been noted in the paper of how terahertz time domain spectroscopy is capable in the detection of mutations and conformational modes of biomolecules. This paper also discusses about the method of label-free probing of binding state of DNAs, and it also discusses that the terahertz imaging will likely find use in wound assessment. This major limitation, which was highlighted in the paper, was that the terahertz imaging is a slow process. Furthermore, the radiation of the terahertz pulse is absorbed by water and thus do not penetrate moist tissues at any significant depth. Terahertz imaging, this corresponds to features in the range 1 micrometer to 3 mm, not detailed enough for many medical applications. Uh, there are, however, ways to overcome this, and the foremost among them is a near field imaging. The drawback to this technique is the proximity in which the sample must be placed to the aperture. A distance of less than 1 mm is required for frequency of 300 GHz and above, which make the technique impractical for in vivo reflection mode use. Review for the paper 4. This paper produces a method for generation of terahertz generation in lithium niobate using reflective stair step echelon structure. In this method, echelon produces a discrete uh, tilted pulses with less angular dispersion compared to high groove density grating. This paper states that the conversion efficiency of the tidal pulses front techniques is very less in the experimental setup. Peak conversion efficiency at uh, cryogenic temperature was 0.33%. It is stated that the short pulses are often desirable in nonlinear terahertz spectroscopy measurement or for electro-optic sampling. Increasing the transform limited duration is increased by filtering would come at the cost of the overall system of both time resolution and reduced optical pulse energy. It has also been proposed and demonstrated imperfect imaging reduces the effective generation length compared to that reached by imaging of the beam for a typical grating. Furthermore, this still requires the use of highly dispersive grating that leads to limited generation length, especially when using pulse with considerable bandwidth. For the next review for the paper 5 and 6 and the conclusion, Jeet will handle. Thank you.
So now I'll take you on the paper review of the paper 5 and 6 and the limitations and the conclusions. So the paper 5 review. So the paper 5 actually discusses on the terahertz pulses generation by the tabletop devices, which are electroconductive switches illuminated by ultra short laser pulses, and the optical rectification of ultra short lasers pulses to nonlinear crystals. So this is investigated in this paper that terahertz generation of terahertz pulses via optical rectification in the linear in the LiNBO3 with various magnesium oxide doping levels is also discussed the pulse front tilting for the phase matching. It also discussed the proposed system as actually reduces the effective velocity of the terahertz wave. This operation also shows that the generation is actually reduces the efficiency or the quantum efficiency of the system by 3.4%. This also says that the experiment this also shows that the experimental setup is the technique of the velocity which is matching the other materials, and the frequency is generally very less compared to the experimental results. On the paper 6 is actually again the generation. It also shows how the terahertz pulse is generated, but this actually the accumulation of all the papers which we have discussed before, and this actually strengthens those points, and it says that the cascading effect with the absorption techniques through angular and material dispersion and techniques is the main causes for the major limitation of the drawback for the generation of terahertz pulses using optical techniques. This paper also provides two approaches for the generation of terahertz radiation. That is the criterion of the ultra fast photocurrent in the photoconductive switch, or a semiconductor using electric field carrier acceleration and the optical heterodyning approach. So terahertz radiation can be generated when the frequency difference happen between both the closely spaced laser modules. So the thing is that now I will take you to the conclusion. So the field of photonics has been extensively used in the field of generation of terahertz device in the designing of terahertz devices, like the development of the quantum cascade laser and the uni traveling carrier photodiode. The terahertz radiation has also got loads of applications in the field of from starting from security screening to drug detection to the semiconductor wafer inspection and to air pollution. The terahertz emission is also a function of frequency, which is a majorly generated by two methods, that's optical rectification and the linear optic effects. And the major limitations which has been taken up because which says that what is the limitations of optical generation of terahertz pulses are the angular dispersion, material dispersion, absorption, non-linear coupled interaction of terahertz and optical radiation, stimulated Raman scattering and stimulated Raman scattering, and the cascading effect in conjunction of the angular dispersion is actually considered as the major limitation for the optical generation of terahertz pulses. And with this, I will conclude our presentation. Thank you. Hopeful to get some good feedback from you and with some constructive questions. Thank you.